Yeah, it's now recording. So today we're going to do a simulation. Let's just do the one for 2024. Let's see. 2024 paper B. I just oh really. So it's a simulation. Okay. I did this question paper in my semester test too. Swarm intelligence. The Utopian Robotics Association has asked you to create a simulation demonstrating the ability of robots to operate independently and as part of an alliance. Okay. When a robot spends too much time operating independently, it runs out of electricity power and becomes dominant. It runs out of electrical power and becomes dominant. It's going to be hard. So robot depends when a robot spends too much time operating independently, it runs out of electrical power and becomes dominant. On the other hand, if a robot follows one or more robots, it becomes allied and never runs out of electrical power. Really. Okay. On the other hand, if a robot follows one or more robots, it becomes alive and never runs out of electrical power. Okay. So we have a solitary robot with the what's this? The exclamation mark. And we have an allied robot with a at sign and an inactive robot with a hashtag. So you must create a simulation that takes place on a two-dimensional grid. All right. Because this is a simulation, there is no player control character. Because this is a simulation, there is no player control character. The simulation begins with robots that are randomly positioned on the grid. Okay. All the robots began as solitary robots. At each turn of the simulation, a robot can either move randomly or follow another robot. So all the robots began as solitary robots. Okay, sharp. At each turn of the simulation, a robot can either move randomly or follow a robot. Okay, sharp. If a robot moves randomly, it will remain solitary, which uses electrical energy. Otherwise, if it chooses to follow another robot, it will become allied with that robot and move in the same direction as them, which does not use electrical energy. Hmm. The decision to join another robot or remain solitary depends on a predefined probability. If a robot becomes solitary for too long, it runs out of energy and becomes dominant. Dormant. Oh, it becomes dormant. You must place the logic of the game in the robot space. Okay, let me create uh, the project. Solution. 2024 paper B. Paper B. Okay, I'll start by doing the linkings. This is Robert space and namespace, Robert space. Then I have my namespace, Robert space. Then in here, and yeah, I will include my robot header file and using namespace robot space. So yeah, that's my linking. Okay, I've done my linking, so everything is Moja. Okay. Alright. Initialize the size of the world, number of robots, and probability of joining a swarm are provided as command line arguments. Ooh, well. So let's overload our main function. We have int axi, then char, peta penta, ax, then let's declare our function to generate random numbers. Let me call it generate random, passing a lower bound and an upper bound. And function for converting strings to integers. Okay, we have to have hashtag include stream and hashtag include stdlib. Then hashtag include ctime. Then other things will add them as we go on. All right. In range, it goes to lower minus this goes to upper minus lower plus 1. Return rent modulus. Then rent modulus range plus lower bound and the function to convert strings to integers. we have num, return num. Okay, string stream ss string num if ss dot fail and fail to convert string num to an integer. And exit. Let me declare my enum for what this for error codes. And we have error valid number of arguments minus 2. And we have error for converting random number, converting strings to integers. Then we have success. That's all. Just going to use error convergence. Okay, and that's all our function. That's our functions. Then yeah, I'm going to use a session to make sure that we have the correct number of arguments. So the arguments must be the number of rows, the number of columns. So the number of rows, the number of argument, the number of columns, then the number of robots, the probability of joining a swarm. Let's make it 20%. So my number of arguments must be 5. So I'm going to use a session. So if I ask if axc is equals to axc must be my number of arguments must be 5, otherwise invalid number of arguments should be rows followed by columns followed by robots and followed by probability. Okay. Probability. And yeah, I'll set my random numbers. That's right. Time at 0. I would now have to climb upstairs in the car. Right, so far so good. Let me prepare my rows. Convert to integer. This will be x1 and followed by the number of calls. Followed by number of robots. Do you think we do something about it? Robots. And followed by the probability. Probability.
The creature to whom it belonged died 300 years
Yeah.
ago. Curiosity is on the far side.
This is not fail. Forgot to open the brackets and stuff. And yeah.
Because we have been told about
So the size of the world, number of robots. Okay, we did that. Pass them through the command line argument. Then they're saying the world is filled in the following order. Solitary robots are scattered across the world randomly. Remember that the number of solitary robots is provided via command line arguments. Okay, we're getting in now. So as always, let's use a record structure. So struct a world in rows, int columns, and we have the 2D array. So call it the grid. Then we have, let's call the number of robots. No, we will figure it out later. Let's start the probability. Int probability. What else? I think that's all. Then we'll make it. We make a function for setup. Setup, and we pass world my reference world. Then we pass in number of rows, number of calls, and the probability. Probability. Okay. Okay. Oh, immediate. No. Okay, let's have world dot rows. Goes to rows and world dot calls. Goes to calls and world dot probability goes to probability. All right, let's come here and declare our record structure. I'm going to call it world. World. Then let's set up our world. Set up world. Okay. So they're saying the world is filled with in the following order. So solitary robots are scattered across the world randomly. Remember that the number of solitary robots is provided via command line argument. Okay, let's have an enum for these features. So int features or characters. We have a space, and we have solitary robots. Then we have we have allied robots, and we have domain. We have domain. We have domain inactive. Let me call it inactive robots. So these are our features. So we do char characters. This is equals to is a dot. That's solitary thingy. displayed by an exclamation mark. Where is that? Not here. Then allied is a net sign. Then inactive, it's a hashtag sign. All right. Then let's make our function to initialize the world. Initialize the world. We're just going to pass the record structure. And while we are at it, let's make the function to allocate memory. Allocate memo, passing the record structure. Allocate memo as the record structure. Then display world and pass the record structure. Okay, that's all for now. So let's go implement these functions. So for the initialize, we just place spaces. We have so for the initialize, we have to pass the number of robots. Number of robots. Okay, we're going to loop through our world, our 2D array, world dot rows hash int r is equals to 0 and r is less than world dot rows plus plus, and for int c is equals to 0, c is less than world dot cows c plus plus, and world dot greet at r and at c is equals to space. Right. Then after placing the spaces, let's place the solitary robots. Just going to use a for loop. So int r is equals to 1 and r is less than or equals to num robots in r plus plus. And they said they're scattered randomly across the world. So let's have int. Let me make this. Let's have int. Let me make this r capital letter R. And here let's generate the random first is the random location. So we have int r is equals to generate random. The lower bound is 0. World dot rows minus 1. And c is equals to generate 0 world dot cows minus 1. And before we place our what's the solitary robots, we must check if we're not placing the solitary robot on top of another solitary robot. So world dot grid at R. Let's see if it's not equals to space, and we gotta generate a new random column. And now we can place our solitary. And yeah, that's the initialize function. Let's allocate memory. So allocating memory, we like world dot read equals to new int pointer, then world dot number of rows, then world dot grid at R equals to new int, then this is world dot number of cows. Okay, that's our allocate memory function merger. Then for the allocation, going to loop through our array, our grid, our rows, then we delete. Then afterwards we delete the whole grid. Okay, that's our deallocate memory. Then for the display, we're going to loop through our world and going to say cout, going to use our array of characters.
Thank you. You need to get
Then yeah, we're done. So let's allocate memory. As in the world, that's the world. And let's deallocate memory. As in the world, and let's initialize our world. As in the world and the number of robots from the command line argument. And let's display the world as in the world. Setup. I forgot to pass the probability. Setup. We pass the probability. Oh, setup. We pass the world, the rows, house, and the probability. Okay. And this is the world so far. We have 5, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 solitary robots. You can see the 20 is for the probability. Oh, the world is filled in the following order. Solitary robots are scattered across the world randomly. Remember the number of solitary, blah, blah, blah. Before we continue, everything clear and stuff. Right, let's continue. So when each robot is placed in the world, we start with n power units. N power units, where n is a random integer in the range 7 to 23. Right. Ah, when each robot is placed in the world, we start with n power units. So we start with a power unit. It means each robot has power units, right? So each robot has power units. So the power units start at a random number between 7 and 23. Huh. So what we're going to do is that in our record structure, let's store the list of our. So let me do this. So I'm going to make another record structure. So this record structure is for my robots. Let me call it struct open the struct robot. And it's going to define a robot. So I'm going to store the location of the robot int r in C is the location of the robot. And we're going to store n for the power unit of the robot, right? So we store its location and the units it has. So in the record structure of the game, we're going to have a list of those robots. So I'm going to use a vector. I think you can use an array. I'm going to use a vector. A vector. What do you do this? A vector. We say vector, then we place in the type. Then what else? We without the name. Let's call it robots. Is this the way we declare the vector? I think for the vector we must have let's take include vector. So yeah, we're going to start the list of the robots. So robot is it has a the its location R and C and N, right? And I'm going to store it in the record structure of the game world. So this is the way we make the vector, or we also forgot. Let me run and check if that's the correct way. Yes, shit. Okay, run. Same is correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in my setup, I'm going to pass the number of robots. Okay, let me let me in my setup pass the number of robots. Setup. Wait, what I'm going to do in setup. So let me in my game world, let me make a variable to store my number of robots. Robots. Then in my setup, I pass the number. robots. Int num robots. And let me also update this thing in the data file. And yeah, I just set my number of robots. Is it number of robots? Goes to num robots. All right. And here I want to pass my number of robots. So under initialize, remember under initialize, that's where I place my robots. So if you check here, initialize, so there's no longer a need for me to pass the number of robots because I'm storing them now. So I'm going to cancel that. No longer passing the number of robots. Then here I'm going to use the number of robots from my local structure. Okay. Right. So in my initialize, so here I'm going to be passing, I'm going to be placing my robots. So each time I pass my robots, so I'm going to also add the robot to my list of robots. So this will be, I think, world dot robots. How do we add? We say, what's that? What's the word? We say push. You use this thing, push back. I would say something like that. Push back. Oh, I'm going to declare a temporary robot structure. So struct robot. I'm going to call it temp. I'm going to say temp dot r is equals to r and temp dot c is equals to c and temp dot n is a random number. Generate random. So is a random number from, is it from 7 to 23? From 7 23. Okay, then afterwards I'm going to push it back to in my list of robots. Let me check if that's the correct way to do it. Ah, that's the correct way. So okay, this is the way to do it. So again we have a list of robots. So first of all, I'm just going to make a temporary robot, then set its location, then generate the random thingy. What's this number of units? They say it's a number of power units. It's a random number from 7 to 23. I'm going to set it. Then I'm going to add my robot to the list of robots here. So seems to be fine. So is there any question before we continue? Question. So we can pass, right? Learning, okay, sure. Okay, let's pass. So when each robot is placed in the world, it starts with n power unit, where n is a random integer in the range 7 to 23. Okay, I've done that. Ooh, movement. So each robot moves one location at each turn. The next location for the robot is determined as, as follows. So let me make a function for movement. So this is void move, movement. I'm just going to pass in my request direction for now. Then also the option. I'm not sure if there should be an option. I will cancel it if there is not. There shouldn't be an option. And for now, I'll use an option. But then I got it. So this thing, the robots move one location each time, right? The next location for the robots is determined as follows. If the robot decides to remain solitary, the robot moves one step in a randomly chosen direction. Okay. So remember we have a probability. What is that? Probability for a robot to remain solitary or join the swarm. Oh, probability of joining a swarm are provided in the command line argument. So, okay, we're going to look through our world first. Going to look through our world. Oh, there's no need for this. Let's look through our list of what's this list of robots from int r goes to 1. Does the vector start at index 0 or start at index 1? We don't know. So let's kind of equals to oral dot robots. This is dot size. Yeah, dot size, and this will be r plus plus. Let me check something. Display. I'm going to display these things and check if they are correct. And r I'll display it's oral dot robots at r dot. Hey, how do you access the thing? Do you access it like this or we use? How do you access it? In one, 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 in one. Hey, I don't know. Let me search. How do you access what? You don't know it. Okay, so vector, blah 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 blah. Auto, hey, auto, IT, begin plus 2. Finds the third element. Oh, notes more. Karena jauh. Oh, so we use the square bracket. Okay, we use the square bracket. This R. This should be dot. Let me say uh, struct and say temp or it's equals to the world dot robots at R. Okay, then here I'll just say temp dot R. Just want to see if it works. J. Check. So this is invalid use of member. Gonna we have what is number of member? Let me use the number of robots. Okay, I think sure now it's working, I guess. So at row 5, here's row 5. 1, 2, 0, 1, 2, 3, 4, 5. Column 13. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So yeah, it's working. Then we have the power unit is 14. Then the next one is at row 1, column 17. Oh, it's at row 1, column 9. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, with 17. The next one is row 15. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 at row 1. So it's this one. Okay, okay. So it works. Which one? 0, 0. Do we have an N? Shouldn't have. Let me check how many are these. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It does this one have 0. Let me check. Oh, so we said this is from 7 to 23. So maybe it means this thing starts from 0. Let me check if it starts from 0. Okay, from 0, and this will be, so yeah, that means the index has some zeros. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So it means yeah, everything is shush. So what are we doing in movement? They're saying in movement, they're saying if the robot decides to remain solitary, the robot moves one step in a random chosen location. Okay. Hello. Renzo. Yeah. Yeah, ke ka rasa shen. Ka rasa shen. Sure. So yeah, lagu sih sama sebab itu. Do you understand it? Mas? Apa? Aku cari pilih-pilih buat kali marau-rau. No answer. Okay. So Shapo. So Shapo, I'm just going to look through the list. Then Shapo, the list of the robot. So when we get to a robot, the robot decides whether to remain solitary or to it decides to remain solitary, the robot moves, or if the robot decides to remain solitary, the robot moves one step in a random choice. Okay. So let's say if so I'm going to generate a random number. So generate a random number from 0 to 100. So if the random number is greater than or less than the probability or probability. So let me say if it's greater than or equals to the probability. If it's greater than or less than, if it's greater than or less than the probability, it means it decides to join the swarm. Else it remains solitary. Okay. So I think we must save, like something that will. I really remember the robots might not be solitary. If the robot decides to follow another robot, then that means the robot must find an empty location in the direction of the robot being followed. If an empty location cannot be found, the robot must stay in its current location and wait for the next turn. The decision to follow another robot or remain solitary depends on the probability provided. Okay, okay, let's leave it like that. So it's either the robot joins the swarm or the robot or does it remains solitary. So if it remains solitary, if the robot remains solitary, the robot moves one step in any random chosen direction. Okay, let's move it to any random chosen direction. Okay. Oh, so already we know we have its location it is at int r and int c. So let's oh shit. What was this? This was temp. So again we are storing it here. Already it has its location. We know its location is temp.r and stuff. So we're going to declare tr. This will represent where this thing is going. So this will be equals to temp. Okay. And let's say okay, set it to remain solitary. So now it must move, but then it must move one unit to any direction. So how are we going to implement this? So it's today it's not possible to use the absolute thingy. So let me try to think of another way. Mm, so another way to do it is to say this is also the location generate random number from -1 to 1. This is another strategy. I know I'm always coming up with new things. This one is hard to explain. So this thing, I remember we know the location of this robot. It is at temp R and at temp it is at R and C. I here we're just storing the current robot. Then we're just using temp for to work with that robot. So to get that robot's location, we use R and C. So sorry. So since this thing has decided to remain solitary, so they're saying if it decides to remain solitary, the robot moves one step. So to make it move to a random location one step. So this is another strategy to do it. So let me let me explain it. Let me try to explain it. So let me make an example and say, so if this we are at this robot, then this robot decides to remain solitary. So it's going to generate a random number TR. So let's say R is this is row number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is row 13, right? So it's going to say row 13 plus generate a random number from -1 to 1. So if that random number, let's say it's 1, if it's 1, this will be TR will be 13 plus 1, which will make it 14. So 14, row 14 is this one. So it means it will possibly move down. But then if it's maybe this random number is -1, this will be 13 minus 1, and the answer will be 12. And 12 is the row above. Right? Is the row above. And for C, this is column number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is column 12. So here we're going to generate a random number. So this will be 12. Let's say this thing generates a 0. So TC will be 12. Okay, let's say this one it's generated 14. Let's say TR is 14, then this one becomes 12. So let's say this is 13, and let's say this random number is -1. So TC will become 12, right? So if TC becomes 12, it means you're going to this column. Then if TR is 13, we're going to the column above. So you see this thing will move to this location. This is hard to explain, but then this enables us to only move one direction from the current location. So before I move, I'm going to check. Before I move my solitary, I'm going to check if I'm within bounds. So TR must be TR must be greater than or equals to 0, and TR must be less than or equals to world dot rows -1, and TC For it to be within bounds, it must be greater than or equal to 0, and TC must be less than or equals to world.row.cost minus 1. So here I'm just checking if I'm still within bounds. So I'm checking if my row is within bounds, and I'm checking if my column is within bounds. If it's within bounds, then now I can move. I'm going to say world dot grid at tr and at tc goes to solitary. And I'm going to update my, this will be temp dot r goes to tr, and this is temp dot tc goes to, going to be tc. I don't know what happens to the n. Tn is for this thing. I think maybe it increases by 1. I'm not sure. Let's just decrease it by 1. So how am I going to edit back? So to edit back, so this is world dot robots dot, I shouldn't do this. I should say push back. So I'm going to push back this new one temp. But then remember, we still have that old one. So before I do this, I'm going to remove that old one. So it's world dot robots. I don't know, remove. And I send what I want to remove. I'm not sure if you send the, let's check if you, when you want to remove something from the thingy. Oh, use add. Let me check if how to remove something from the list. So to remove, so to remove here, pop back, I think it removes the one at the back, and erase. I don't understand it. Then remove a range of elements, remove element at a specific index. Oh, this is the one. At a specific index. Let's say, let's use erase. Erase. Oh, what? Erase. Then index is index R. So I'm going to remove the old one, then we push back the new one. Okay, and I think that's how we if the robot decides to remain solitary, the robot moves one step in a randomly chosen direction. Okay, so we have done that. And if the robot decides to follow another robot, the robot moves one step in the direction of the robot being followed. This means that the robot must find an empty location in the direction of the robot being followed. If an empty location cannot be found, the robot must stay in its current location and wait for the next turn. Okay, let me highlight this point. The decision to follow another robot or remain solitary depends on the probability provided as a command line argument. So remember here, so this thing can decide to follow another, what's this? Follow another, can decide to follow another robot. So how do we know if a robot moved or whatever? So let's pass it for now. But then let's just do it one way. So we're going to, so in this thing, in this in each robot, we're going to store the index, the index, the index, the index of, in case a robot decides to follow another robot, we're going to store the index. Oh, let's just store. This is difficult. So I was going to say let us store the robot which the current robot is following, and then it will be complex to do that. So let's just store the index in which the current robot is following. So int r will represent the robot, the index of the robot that's being followed. Okay? So like this current robot, the R here will represent the index of the robot that is following the current one. Or is those this let's just make it the index of the robot that it is following. Okay, that is following. Okay, and then how do we know if the robot has moved already or what? So I'm going to say int rr. So int rr will like I already remember a robot moves only one direction. So this one will store uh will store oh, so if you check here, I'm generating a random number from -1 to 1. So this this rr will just store this random number here, and RC will just store the random number that has been generated here. So this RR will tell us where the robot at index R moved using this RR and RC. So it means here I'm going to say mm, so I have to store whatever is generated here. So the way to store whatever is generated here, I'm going to use an if statement. Let me check it. I'm going to say if tr still remained temp.r. If it remains the same, it means the random number was 0. So temp, so it's like we're storing the movement we're going to store the movement of each robot. So this will be int r equals to 0, then else if this is tr minus 1. So if it's tr minus 1, it means the random number was minus 1. So this would be temp dot, I'm supposed to say rr, and else if this was tr is equals to this thing plus 1, it means that random number was 1. And we're going to do the same. Yeah, this is 1. So we're going to do the same with the column. This is tc times tc c c c c c. All right. So here's like I'm storing the movement of, I get here you decided to move, so I'm storing its movement. So with this RC and RR, I will know where it moved. So here, if this thing decides to join to follow another robot, so I'm going to choose a random robot. Let's say, so we're going to say int r equals to generate. We're going to choose a random robots. So from 0 to, let's use r, from, r minus 1. So I'm going to choose a random robot. I'm going to choose a robot that has already moved. So that's the reason why I'm saying r minus 1. I wanted to choose a robot. Oh, this is 1. Oh, yes, it start from 0. So I wanted to choose, I am saying r minus 1. This is, I can't say int r. Let me say index. And here I can use r. So I want to generate a random robot, a robot that has already moved. Okay, so I'm going to generate it index here. The reason why I'm using r minus 1 is because, let's say we are at robot 2. So I want to choose a robot that has already moved. So obviously the robot that's already moved is will be between robot 1 and robot 0. Okay, then I will generate the random row and the random column. Oh, I will now say, I'll get the, let me get the robot, struct robot, and temp goes to world dot robots at index. Okay, then I will get uh, the movement of this thing. So this thing will be temp. This will be, I can use temp twice. So this one will be Let me call it following, the one that we're following. Then here we're going to say temp dot r, then we're going to plus following dot rr. And here I'm going to say temp c plus following dot rc. Okay, then we're going to move this robot to the same direction as this one. But before we move it, we must check this thing. We must check if where it's going is within bounds. Okay. Want to erase it. Tr. Then I think we must also store the also its movement. So we must also store its movement also. So the movement, we will know the movement is the same as this one. So we're going to say temp dot rr. So here instead of saying index, okay, this is rr following dot rr, then temp rc equals to following dot rc. So yeah, this should work. Let me check if it makes sense. I think it makes sense. If it doesn't make sense, we will let me check something. No matching function to call erase. So we'll erase what we're supposed we only pass the index, right? Yes. Remove element at a specified index. We use erase. Beginning, this will be 1. Okay. Let's check another way to remove this thing. Remove specific values. Erase, remove item. Let's just use a remove. But when we're using remove, I think we're just going to pass the temp. If we use remove, we just pass in the temp. Let's check if remove works. It also doesn't work. Mm, let me do this.
Means to be in more aggressive when they have the ball in one season, change which the sensation was not the sensation for right now is no good. So they need to check that they're getting it's like we're seeing what they have out. So to get in the game.
Ah, algorithm. Second good. This is still at remove. So when we remove, something, we must say world dot robots dot begin and the index. And also this side. That's the only error in this one. Let me show you if this one works. Okay. Supposed to be dot remove. Alright, let's check if this thing works. So if a robot remains solitary, loses one power unit for that turn. We did that. So if he only loses one unit if it remains solitary. If a robot decides to remain solitary, so if the if statement for remaining solitary is this one, so we did it. This if statement is for it to remain solid. The probabilities for joining a swarm. So yeah. So this side we did it. We did it here. Then if a robot remains solitary, it loses one power unit for that turn. If the robot's power units reach 0, the robot becomes dormant for the rest of the simulation. So maybe I can say I can check if my number and if n is equals to 0, then make it a dominant. So if term dot n is equals to 0, and it means must This one I will do it here. So I'll say if n is close to 0, I'll make this thing dominant. Dominant. I made it dominant. I represented by inactive. Active. And yeah, else. So if it's dominant or inactive, we don't need to know. Don't need to move it or stuff and stuff. Okay. If a robot chooses to follow another robot, it becomes allied robot and does not lose any power of energy for the current turn. Okay. I removed the losing of energy here. So let me check something. End of simulation. The simulation ends if there are no solitary. So the simulation is the one that's going to be hard. Do while let me add a status in here. Let's just use Boolean continue.
Like they're staying in the position, they don't move. So it's so difficult. They're getting shoes like that, they don't even hey, no, no.
Okay, so and move it in here. We will display our world. Before we display it, we first thing we clear the screen, CLS. Then here maybe we use a switch. Let's display the menu. The menu I think is only two choices. Let's just say choose T for 10, then Q for pit, and yeah, scene, scene, option. I'll just make a switch, convert to an uppercase, upper. We're going to have case T, case Q, and the default. Invalid option. And pause. Okay, if this is Q, then you say C out, leaving And line and Boolean continues also false. Yeah, and there's no need for me to pass an option, so I don't use it anyway. So here for movement, I will remove the option. Let me check what this thing does. Let me check what it does. As SAT, you see the thing moves. Okay, it's an error. This is the switch. Okay, move. Mm-hmm. Yeah, let's deal with movement. Only let me check if the thing works. G invalid. Okay, then Q. Yeah, leaving. Those ones works. So let me make sure. Mm-hmm. Everything should be fine here. Shit. Enter. Okay. This is the simulation. You can see. But then it doesn't work forever. Somehow it crashes. Which we have to fix it. But then it works just a few times. Okay, okay, okay. You can see these things are increasing. Then somewhere it crashes. So I'm sure where it crashes is where it goes out of bounds. Oh, what am I going to do? I'm going to under movement. Under movement. Ash. Oh, wait. There's something which I'm forgetting. Okay, this one we did it correctly. So movement. So each robot moves one location at each time. The next location for the robot is determined as follows. If the robot decides to remain solitary, the robot moves one step in a random chosen direction. Okay, sharp. Here we're just looping through our robots. I think there's a point where this thing is supposed to use the dot size. I'm not wonder why it's not working. So world dot robot dot size. That one should work. Yeah, the size thing works. Let me check something. Somewhere it still crashes. Okay, sharp. At least this thing works. So, all right, we're looping through our our list, right? Okay, this is correct. Then we're saying if the robot decides to remain solitary, the robot moves one step in a randomly chosen direction. So in our list, we're only going to store solitary. We're going to store solitary only. Okay, then sharp what then we're going to use temp to store the current, going to use temp to store the current, what's this, the current robot. So temp will be the current robot. Then we say if the robot decides to remain solitary, the robot moves one step in a random chosen direction. So the robot, if it chooses to remain solitary, I rate this one is for joining the swarm. Remember, when you join a swarm, this will be determined by using the probability. So I want to do this. I want to comment these things out, and and I first deal with this one for if for if for if a robot decides to remain solitary. I just want to check if how it works actually. So like those things must not increase; they must just move around only. So I'll check why they're increasing. Okay, we don't have an error in our in this side of the decision to remain solitary, but then we must do it right. So the robot moves one step in a random chosen direction. So this thing must only move. It must not create another robot. It must only move. So okay, so if the current thing decides to remain solitary, here we are generating the random location, right? Location for movement. Okay, sharp wood. Location for movement. Then here we just store uh, the way that robot is moving. So okay, if this is equals to temp dot r, it means this one was 0. Okay, this is good. This is good. This is good. Okay. So here there's no problem. We're just storing how the thing moved. So what about the if statement? So under the if statement, we're checking if where the thing is moving, if it's within bounds. So if it is within bounds, so this thing here, I was using it to erase the current robot. I just want to remove it from the world. So to remove that one, we use this thing. We use robot erase. Then we say world.robots.begin plus r. Okay, so that's how we remove it. Then here we're going to edit again. So we're going to say temp r is equals to tr, temp and c is oh, I know what the problem is. So remember, we're just placing the new robot, but then we're forgetting to to place a space where the previous robot was. So yeah, so here we're just updating the location of the robot. Then we must decrease its number of power units. So if the number of power units are equals to 0, this thing becomes dominant. It becomes a dominant robot. Okay, that's fine. Then else if this thing moves, so here you must also say where I get this thing is moving, then where it moved from, where it was, we're going to place a space. I think that was the problem. Going to place a space where it was. So ish, where was it? It was a tr, and this is going to be plus. This is temp dot. Oh, where was it? It was at this. So it means we must, before we update this thing. So we must update this thing afterwards. So this one will become dominant and it does not move. So here we say, okay, let me move it. Not great. At temp.r, temp.c goes to space. This is where it was. Let me check if this one works correctly. So the robot must be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They must only move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something is still wrong. So connecting. Okay. So here we're saying else. Then we're checking where the thing was. So if it was here, we're going to place a space. Then where it is moving, we're placing the solitary. So what could be the problem? Moses. The space is the dot. Okay, let me check what's wrong here. Something is definitely not right. Let me just say exactly. They're increasing. I don't want them to increase. I want them to increase. Let's check. So this is int tr. Oh, let me check. if everything is right here. This side, everything is good. There's still people here. So I don't want to move. So here, I first check the location where I wanted to move. So okay, sharp, I generate the random location. So this is TRTC, and here I want to update the movement. Sharp, I'm updating the movement here. Also for the TC, this is good, right? Then I'm checking if this thing is within bounds. Okay, then here there shouldn't be a problem. I'm removing the current robot from the list. So if I'm removing the current robot from the list, this shouldn't be a problem. Then I decrease the temporary the power the unit the power of unit. So I decrease it. Then I check before I place the thing. I check if it's zero. If it's zero, where this thing is going, I'm making it inactive. This should be temp.r. This should be inactive. I don't want it. This this will be if it equals to zero. So here, let me add this thing. Oh, T. Oh, wait. Okay, this one will be okay. Temp at R temp C. Okay, here we'll put a space, and here we'll put a solitary. Okay, sharp. Here we're checking if this is within bounds. Then we erase the one. Then we check this. So if the n is equals to zero, this thing doesn't move. It remains where it is. That's why I'm saying that. Then here we place a space. Okay. Then we move the solitary. And now we then here these things must be before must come here. Okay. So here we're removing, but then the study falls. Team springs into action, setting up their own Ghost Lab version of Shawnee on the Heart. Very frank. Tyson, which way? It goes, the other day, and then it's like, I must add this thing afterwards. So here I'm making that thing inactive, but then I'm not updating its location. Wait, and this should remain there. And for this one, in here, temp R and temp C must remain the same. So I think I should remove this. So as it's still 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Welele. But then they're not duplicating. They're not increasing. They're just moving. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I crazy? Then this one came dominant. This one became dominant. So from now on, they will not it never move. Or it shouldn't move at all. Yeah. You know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So here I'm going to check the n. I'm going to check if temp dot n is greater than or equals to 1. If it's greater than or equals to 1, that's when I decrease it. I 1. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another 10. Remove this one. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's still 10. Then it moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's still 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Okay, this one became dormant or inactive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these ones should, from now on, they should never move. They should remain the same until. Okay, they're not moving. Yeah, then I think we're good to go. Then if in the world there are no, what are those things? There are no longer solitary solitary robots. Then that's when the game ends in defeat. If a robot, this one, then the solution ends when there are no solitary robots in the environment. So I will add a function to check for that. I'm going to say, wait, how can I check it? Let me just have a function. Void check solitary. I'm going to make it a boolean. I'm going to make it return a boolean. Okay. So going to loop through the world. Through the world. And if world.grid at r, let's see if there is a solitary robot, then we return true. And if there's if there's no solitary object, we return false. So if there's a solitary robot, this thing will return true. If there's no solitary, this thing will return false. And where should I check it? I said I check it. The simulation ends when there are no solitary robots in the environment for that turn. So I must check it after every turn. So maybe I would say, what is that? After like a movement, I check. Let me say bull, check. Can say check solitaire, and I'm passing my one. So if this thing, if if check is equals to, if it's true, it means that's still. But then if it's false, it means there are no solitaire. So I'm going to see out simulation and don't mean then oof, then boolean must now be equals to false. So it seems like a great idea to save boolean status here. Status, and I'm going to say world.status equals to false. And I'm going to set status to true in the setup. Favorite to false, right? Then in here, I'm going to cancel boolean continue and going to use world.status. All right, this will be world.status. Okay, something is wrong. So if check is so if this is equals to false, it means if it's equals to false, it means there are no solitary. Oh, no, this is a return. Hey, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10. So I forgot to include. You see, I'm checking if this thing is within the world. But then, what if it's going to a place where there is something like, and you can say world dot grid. This must be equals to space or grid at tr and at tc. Where the thing is going must be equals to a space. But then, so far there was no effect. I don't know. Okay, it's moving. 1, 2, 3, 4, 5, 6. Yep, 1, 2, 4, 6, 8, 10. Okay, that remain dominant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. Okay, but I took this one. Let's see how long it will move. Okay, just that it doesn't update first before it. So this one will become dominant, but just that it doesn't display the thing first. So maybe I could make it display the thing first, or maybe I can do that. Let me do this. Let me say, let me do clear the screen and display the world so that we can see it. We can see that really there are no what's this? There are no solitary objects in there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I should stop counting now. It works. Okay, you see it returns 0. Oh, let me, after it displayed, after it displays the screen, let me do this. Let me display the message. Simulation ends. This is under where you check if they are still solitary objects. Oh, I moved. I cancelled that thing first. Yeah, you see, you can see everything is no longer solitary. Then you see the world first, then you see simulation ends, then the program terminates. Okay, so we did, what's this? So this condition, we're fine with it if the robot decides to remain solitary. Now let's deal with this one. If the robot decides to follow another robot, the robot moves one step in the direction of the robot being followed. This means the robot must find an empty space in the direction of, yeah, let's implement this one. So it's this else if. Whew. Okay. So as always, we're going to we're going to 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 choose one index. We're going to choose one robot to follow. We're going to choose it randomly. Okay, we got the index now. Then here we're saving it here. We're saying it's equals to following. You see, we're using the index. Then now we want to move the current robot to the same location as that one. So we're going to check how this one moved. See, we're using following RC and RR to check how it moved. So this one represents where it is going. So here we check if it's still in bounds and limit. Let's also check if where it's going, if it's not going to a place where to a place that is occupied. So it must go to a place where there's space. So what do? Here we erase. Why are we erase we erase we erase what we have at the moment. Okay, then we're going to make it this thing equals to we're going to make it equals to solitary. We're going to make this thing equals to solitary. Then where it was, we want to put space. So it's going to be temp. This is going to be temp.r, then temp.c. It's going to be space. Let me put it before. I want to put it before. Then where it's going, I'm going to put the solitary. Okay, but ahead it must be, if it's following something, it must change to what's it changing to to that robot. What's the other robot is allied. It must change to allied if it's following something. So if it's following another robot, I'm going to change it to allied. And they're saying its number of its power, its power units is not decreasing. So there's no way that I'm decreasing it. Okay. Okay. Then yeah, here just update the location, temp R, temp C, and okay. Okay. Then push back. I think everything should be fine. I'm going to comment this one out. Somewhere it's here. Okay. Okay, yeah. I'm going to comment it out. So now so these ones must only move if they are following something else. Okay, no movement so far. Oh, it's not possible. Oh, how are we so dumb? So if nothing is moved, I guess this one is the only the ones this one is the only one that does the movement. So if nothing moves, so it means they're following this thing. They're following this following. When we're checking this thing will just be zero. So it means there was no movement. So we must put them together. So T, there's an error with this one. There's an error with this thing. So wait the but then this one is the only one that's giving us problems. But then let's check. We choose a random robot. Choose a random robot. This might be the problem. Let me say if R, wait, this should be from 0 to R minus 1. If index is less than, so imagine this will be, if R is 0, it means this thing will be minus 1. That's impossible. So we must say, let's just check the rest of the robots, even if they haven't moved yet. Robots dot size. I hope it works now. Okay, so far so good. Oh, you see that one became then allied 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this one became allied. So they followed some other robots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this one then it was an allied. It was, you see, it was here and it was an allied. Then afterwards it decided to move. Then it moved here. Then I think this one remained an allied. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's something which we forgot. So under this one, if a robot is a if a robot is a torment, it means it must not be able to move or anything like that. So if the robot uh, is not inactive dormant, so yeah, because I see that the ones that become dormant, they will move and they are not supposed to move. Okay, okay. So this one's they must remain dormant forever. In by dormant I mean inactive, so they must remain like this forever. Okay, they move. So there's a problem in here. Huh. TC must not be TC. It must be it must be TC. No, I think it must be temp.r temp.c. Let's check if that works. Eh, this one must not never move. If it moves, it still did something wrong. Okay, they're not moving. Yeah, the dormant one are not moving. We corrected that thing. So we're left with 1, 2, 3, 4, 5, 6. Okay, 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 okay. We're left with 1. Yeah, so this is the simulation. So let me check if we've done everything. If a robot decides to follow another robot, blah 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 blah. Okay, this one we did just now. Then if a robot chooses to follow another robot, it becomes an allied. Okay, we just did that. Then and does not lose any power units. Yeah, for the current turn. Yeah, it didn't. And this one it also did it. So that's it. That's the that's our simulation, our favorite tools. So I know it's difficult, but then yeah, that's the simulation.
No, thank you,
Uh,
man. Thank you so much.
so did you guys understand it? Cause we're doing a lot of things, and we just go through the video and check.
Yeah, the video is very useful. It will help us. Yeah.
Yeah, and then, yeah. From the moment I displayed the solitary, that's where you got the marks. It's just that I forgot to calculate, but then that's where you got the marks. The moment before we did the movement, so that's where you got the marks. So at the moment it's total, but then before we did the logic, so it was 100 minus 15. So this movement function, yeah, the one that has these 15 marks, or 10 marks actually, or 10 marks. Right, the output was correct. So yeah, I'll send you this thing. Yeah. Dango, level ushu bobo.
Thank you, man. Learn.
Dango.